Alrighty, and we're live.
All right. We're going to continue our Clay walkthroughs. This time I'm going to be talking about Ford, which is Urbit's build system, and it's part of Clay. And actually, since we started these walkthroughs, Philip actually went and rewrote a big chunk of Ford, completely redid its dependency tracking and caching system. So now it has a global cache, and I helped a bit with this, but Philip, I think, has a much clearer sense of how that part of the system works. So I'm going to describe what Ford does generally, how it fits into Clay, and then Philip can fill us in on how the caching and dependency tracking work. So the general idea is that you want programmers to be able to write files full of source code, have those files refer to the Urbit standard library, which is called Zeus, and also have them import other libraries. Right? So you want to be able to write a library as a user space developer, and then write, say, an agent that imports that library. And then you want Ford to perform those imports and compile your code and put that together into a program, which you can then run as a Gall agent, or maybe you're building some other kind of program. So Ford is the system that does this. So its most basic function is called build file, which we see here on the right on line 912. And build file and build directory are very similar, so they both call out to this helper function called build dependency. So you can see build dependency here. And I'm going to skip down to line 901, because here's really where sort of Ford takes over. The stuff before that is dependency tracking and caching stuff. So the general thing we need to do is we need to read the actual value of the file, which is text, right? It's a text file full of hoon code. So we call read file on the path that we're passed in. And then once we read the file, we have some text for it. Then the next line we assert that that it was actually a hoon file, right? So that it's mark p.cag is send hoon. So was this what kind of file was this, right? So because Clay can store files of different types, right, depending on what mark they are. So the file extension refers to an actual piece of code that determines what that type of file, how that type of file works. So what type is stored at and some operations that can be performed on it. So we're asserting this is an actual hoon file. And then the next line, we convert it from chord to a tape. So just, instead of just an atom as a string, this is a list of characters. And then we parse it, and we parse it to a pile, which is a data structure representing sort of all of the imports. It's like a pre-processed source file, so it has all the imports and then an actual hoon at the end. So we can see on the left here that this is the data type for a pile. So it has all these different lists of imports. So there's about 7 different kinds of imports that you can do. And then at the end, it has a hoon, which represents the actual body of the file, right? So there are the imports at the top, and then there's the body, which is just some hoon source. So so Ford has these build directives. You can see the faz-hep rune for importing a SIR file, the faz-lus rune for importing a lib file, etc. So special syntax for Ford for doing build directives. So it's a nice clean layering, actually, right? Where hoon, the language, has no syntax for builds, but Ford does, and so Ford adds the syntax to hoon, and then you can. So when you're writing a user space file, you're really writing a Ford file that contains hoon as the last element of the pile. So we parse this with parse pile on line 904 on the right there. And then on the next line, we run the prelude, which means that we perform the imports. and this modifies sut, which is our subject. So it's the build subject that we're going to use. So that's the environment that we're going to use to build, to compile the hoon that's in this file. And then we do this, the gain leak line, that's also some dependency tracking stuff. And then 909, we call slap sut hoon.pile. So that's the meat of it, where we're actually, this is calling the compiler. So this is saying, take the hoon that's in our pile and run that hoon, like compile it and run it against our subject. So that's what building is actually, both in forward and actually throughout the system. You take a vase of the subject, so the type and the value, and you take some hoon code. You parse the hoon code into a hoon data structure and abstract syntax tree, and then so once you have that abstract syntax tree, you run it. So this is slap. You compile it and run it against the vase of the subject and produce a vase of the result. So when you're writing a hoon file in user space, you're actually writing basically like a script that just starts from Zeus, the standard library, and whatever other imports you've imported as your subject, and then you're describing an expression to run starting from that to produce the program that you want. So typically it's something like add a core, like wrap a core around the standard library. And maybe that's an agent core, or maybe that's a library core that just has some helper functions in it or some data types. So this is all to say, like, here's the basic thing that Ford does. Right, so you give it, you say, hey, you can ask it to build a file at a path, and so that will look at all of the dependencies, build all those dependencies, and then it'll build your file using the result of those. And so there are a number of different kinds of Ford builds. So I think it might be good to go to the type of the build. What is it called? Mist? No, is that right? Ford?
Yeah.
Right. So let's start with the Mist. Yeah. So these are the different kinds of builds you can do. So we just went through file. So build file has a send file build. So the only argument that it takes is a path. You say which path, which file are you building? The next two, nave and dias, relate to building a mark, which I'll explain. But a mark is the file type. It's a file type that's named after extension.
Right.
So the tis mark there.
Yeah. Notably, all of these are already within the context of a specific desk and a specific revision. So that's why a file only needs a path. It's because we already know the revision and everything. So why we can refer to a mark like on its own, which might mean different things between different desks or revisions or something, but we're already in that context.
That's right. Yeah. So I should have mentioned that Ford operates within one snapshot of one desk. So like one commit, basically. And there's no conception of anything outside of that. And the reason for that is that you want to be able to express an import as just like some path without having to say what revision it is and then change the revision all the time or say where it came from or some other thing. And this also kind of keeps it sane so that when you do a Ford build, that Ford build is a pure function of the files in that snapshot. So there are no sort of hidden inputs to the build. It's a purely functional build system. So the first thing we can build is a file, which we just looked at. The next two, nave and dias, are for building a single mark. And so that's building a file type definition. So what that does is it builds the file that describes that definition. So this will be like fazmar, faz mime, fazhoon, for example, for the mime mark. All the mark definitions are in the fazmar folder. So it'll build that file, do a basic build of it, and then do some metaprogramming to look at, to sort of process the thing that gets built and turn it into sort of like a standard format that the system can use. So Nave does that in one way, Dias does that in a different way. Similarly, cast and tube take in a Mars, which is a pair of marks. And so both of these, those convert a datum from one mark to another. So you might convert from line to text, for example. And cast and tube, those also, one is dynamically typed and one is statically typed. That's also the difference between Nave and Dias. And the last two are leaf builds, Veil and Arch. So a Veil just says read a file at a path. Like, don't try to build it, just read it and validate it. So Veil is sort of a shorthand for validate. So when you first give Clay a file, it's just a page, right? It's a pair of mark and noun. So it says what mark it is, or what mark it's supposed to be, but it just has a raw noun there. So we haven't actually checked whether that noun is of the right type and matches whatever other constraints that the mark is supposed to impose. So Veil actually builds the mark for this path and uses that mark to validate the data there. And finally, there's Arch. And so Arch is a name for a directory listing in Urbit. And so there's a kind of build that reads from a whole directory, the faz-sig. You can import a whole directory worth of hoon files. And so and that'll come in as a map from path to value in your program. And so in order to express that, Ford has to be able to build a whole directory. So that's what Arch is. Or really, it's just, and so to get into a little bit more detail about Veil and Arch, we can see Pour just below Mist, Ford build with content. And so notice that the last two are leaf builds, but here they're augmented with the actual value. So not just the path, but the value at that path, or for an Arch, the value at all of those paths. So the Pour here is, this is actually, like those leafs can be used to be like a referentially transparent request. And we'll get into that more a bit with when we get into caching. But there's a way of expressing a Ford build that says, like, here's a data structure for this build request, and that data structure is enough to specify the result. So unlike a Mist, where if you run a Mist on one revision and then run the same Mist on the next revision, you'll get a different answer. What is it? Is it leak? Is that the name for the referentially transparent request?
Yeah. Yeah, which just includes
right. So that has a for and its dependencies recursively, and so that specifies all of the files and all the values, and then the sort of tree of builds that are run on top of those, and all those dependencies transferably, so that that's a full spec for all the dependencies of a complex build. So we'll get into that part more. So for now, let's go into the different kinds of builds, and I think Veil might be the one to start with after File, because that's a low-level build.
Yeah.
Yeah. So let's see. So this sort of really starts on line 612.
Yeah.
So when we run Ford, we run it with this map of files called files. So first we grab the actual file data. So that's either a page or a lobe files. So when we convert it to a page, by saying, well, if it's, right, so line 616, we say, if it's already a page, right, then just return that. Otherwise, look up the lobe in the file store. So that's also part of forward's arguments. So that's a map from lobe to page. And that's also just passed in to forward. And both of these things they come from the desk, right? So all these pages are already known, right? So the full set of files, at least their pages, those are already specified before we start running forward on anything.
Right. Yeah. That's a good point to emphasize that these are the entire arguments to forward, and forward is not in some desk that has context that can refer to other things. These are the entire arguments to forward. These two things are purely caches, and so the only actual arguments are a map of path to either a page or a lobe. If it is a lobe, then that lobe will be in the file store, so it's effectively a map of path to page. That lobe might be in the file store. Although if it's not, then it's tombstoned. But that's it. So that's the only arguments to forward.
Yeah, and if it's tombstone, then these builds will crash, right?
Right.
Yeah, and so that's actually what the sig bar here is for, saying if this crashes, it's because it was tombstoned, and so it'll spit out an error message saying it can't run the build because I don't actually have the file that I would have needed to run it. So then the meat of this happens in 620, where we call validate page. Right, so this is where we say, all right, we're going to take the data at this path and actually validate it to be of the right mark. So we extract the mark that's Mac from the path. It's just the last element of the path. We have a new function for this, right? Called rear, right?
Oh, really?
Instead of head of flop, I think we can call it rear. Yeah.
Huh.
Kind of funny that we didn't have that in the standard library until fairly recently, but we do now.
Well, there's some kind of principle that you shouldn't put things in the standard library that are slow, which snock and rear are just kind of it almost feels like it should be expensive to call something like that, because it's very obvious from here that this is a slow operation, but also rear is faster than this operation.
Yeah.
So this is more memory intensive than rear, presumably.
Right.
But yeah.
Yeah, I think that's we don't want to incredibly obscure the fact that lists are faster at the front, but yeah. So in any case, we extract the mark. That's the last element of the path. And then there are two cases. So the first case is where the mark where the page that we have, right, the actual data, is tagged with the same mark as the name of the file. In that case, we just call page to cage. Otherwise, we have to convert. So we convert the data in the. So first, we convert we get the typed version of the data that's in the page. Right. So we call page to cage on line 839. Right, and that gives us gives us vax, which is the days of that. And then we also build the tube, which is a converter function from. And so we're going to convert from the mark that's in the page that we're storing to the mark of the name of the file, right? The last element of the file. So the tube there is a gate, and so then we call the gate on our vase, and that gives us a converted value. So if we were storing, something as a MIME, but it's actually a something as text, then when we go to validate it, we'll convert it.
Yeah, and notably, the only time that this happens is when you're committing a file, right? So if you commit a file, that is of a different mark than the path says it should be, then we'll do this conversion. That shouldn't. I don't think that ever happens. Although, like for stuff that's already been, yeah, that never happens for stuff that's already like stored in our object store.
Well, it's a good question actually, because if we do that, we would have to sort of overwrite the page with the resulting page here, right?
Yeah. So
Which I
that's
don't know
what
if we do.
checkout changes is, I think, is the one that's supposed to do that. Yeah. It goes ahead and runs read file on.
It calls read file, which will do this conversion.
Yeah.
So we get a cage out of that, and do we take the cage and so then we run page to load, but p q to cage.
Right.
Yeah.
And
so that's the cage that came out of running read file.
Right.
Right. So.
Yeah. Yeah. So it's notable that this is just a checkout changes. This did not used to be true, but now it is true that checkout changes is just like an optimization. We're trying to eagerly do these conversions, but technically everything would work fine without it even there at all. We haven't talked about checkout changes yet because that's part of the commit flow. But yeah.
Yeah. This is the this is where we go to do a commit, and we basically validate all the files in that commit.
Right.
By calling read file.
Right.
So that's one of the major entry points to forward, and one of the major call sites for read file, right? And read file calls validate page, which is what we're looking at here. So that will get called with something if you make a commit and that commit has a file that needs to be converted in order to match the file, the path, then this will convert it here. And this is usually done for when you got files in from Unix, because those come in with the send mime mark. Right, that's the usual case when that'll happen, right?
Yeah.
Because you get stuff in from Unix, and Unix doesn't have a concept of marks, so it just has a file extension, so then we convert it from a very generic mark called mime to whatever the file actually is. So let's look at page to cage briefly. So assuming we don't have to convert, we'll look at how conversion works, like how we build a tube and call it later. Right. So let's just look at this page to cage first here.
Yeah, I think the most confusing part about all this is kind of how circular it is. So I guess we'll just trace it through and then recap and be like, okay, now I'll go back to this part now that we understand the whole cycle.
Exactly. Yeah. I'm trying to avoid the cycle, right? Do it sort of acyclically in the description, which may or may not be possible. But because there is a strange thing here where
build to build dias, those are all going to depend on read file. They're all going to depend on build file, which depends on read file. They all depend on each other. Yeah.
Right. And so basically, like in 850 there, like when we go to convert a page to a cage, like when we go to actually validate a file to some mark, we build the dias, which is like the mark definition. And of course, in order to build the mark definition, we have to read the file for that mark definition, right? So this is circular. So how do we stop, right? We need to truncate. We need a base case for the recursion. Yeah. So the base cases actually show up right here. So 846, we say, is it a hoon file? And if it's a hoon file, we don't use the hoon mark definition. We just say, okay, we know that a hoon file is always just an atom. It's just a pat t, right? So it's just an atom of text, and that's it, right? So we construct the type in here manually. That's send atom, send t sig. That's the type. So we're making a cage, right? Mark type and noun. And so this is just hard coded, right? So basically, Clay understands hoon code natively. It doesn't have, so that's where everything bottoms out. So you go to read something, and it's some mark. Okay, you have to build the mark, and then to build that mark definition, you have to read that file, but then that file is going to be the hoon file. And so Clay says, aha, I know how to do that. I don't have to check anything else. It also knows how to read MIME files. So that's the next line. So MIME is similarly hard-coded. Right. So if it's a MIME, then we actually have to mic the data to MIME there. So that because to check it, I think.
Yeah, I mean, technically, I guess we wouldn't have to if we just wanted to trust it, but I think we probably shouldn't trust it.
Yeah, it looks like we do trust hoon. Maybe we shouldn't trust that either.
Yeah,
it might
maybe
be okay to trust that one.
Yeah,
because it might be
it might be reasonable
after
to after we validate it.
Yeah.
Maybe. Yeah, I'm not sure.
Right,
It might be that it should at least assert that it's an atom or something.
Right. You could even sane it to that too.
It could, yeah.
Yeah. So in any case, these are the base cases of the recursion. If you hit a hoon, it's usually that you hit a hoon file, right? It's like at some point there's a source file that's written in hoon. Clay just knows directly how to read that.
Right. The only reason you need the MIME one is because the initial commit, is because your commit might come in and the mark that you need or whatever you're trying to read might not be actually stored as hoon. It might be stored as MIME, because it might have come in from Unix, in which case it needs to get converted to hoon. So we need to be able to page to cage the MIME, and then there'll also be a hard coded conversion from MIME to hoon.
Yeah, there is.
Yeah.
Yeah.
Somewhere.
Right. So Clay understands natively how to import files from Unix as MIME, convert them to hoon, and build them. And it can use that as a basis for all the other file types that it understands. And note that all these marks and all these definitions, like they actually have to be in this desk, like in this revision of this desk. For a long time, Clay depended on previous versions of marks or marks from sort of like some set of system marks. None of that exists anymore. And so a desk is this fully contained description of itself, really, assuming that whatever's reading it knows about hoon and MIME. So I think the next thing that's validate page, right? And then the trick. So most of what that does is it builds the dias, and then calls veil on the dias to actually get a typed value, right? So what comes out of veil is a vase there. So I think we should look at build dias, which I believe is just going to call build nav. So build dias is building a mark definition, but that's a dynamically typed mark definition.
Yeah.
And mostly what this does is it calls into it basically calls into the statically typed one and then wraps it in. So it builds a nav and then wraps that in a dynamically typed interface, which is the barcab samtis vase line 716. So
maybe start with build nav then.
Yeah, so we'll start at build nav and then describe the wrapper.
It's worth pointing out, if I missed it, that like that validate page was the last thing in read file. So that the reason why we're kind of moving on from it, apart from it being kind of circular in like to fully understand read file, is there isn't actually anything more to read file. I might recap it at some point, but we are done with it basically.
Right. So we've and so by describing build dias, which calls build nav, which is part of validate page, we will have covered all of read file except for the case where we have to convert from mark to mark. And so we'll describe the just building marks, and then we'll also describe building conversions from mark to mark.
Right.
So in build nav, we should probably pull up. I would say we should pull up an actual mark file to look at this.
Sure. You want to look at like text or something?
Text, yeah, I think text is a good one.
Right. So the most of this is the upgrades, but it's nice because it actually has everything here.
Yeah, so this is a Mark IV. So it's a bar cab, it's a door, and so we're going to be building this with build nav, and then we're going to be transforming it a little bit to sort of follow some of its references and resolve it. So we start by running build fit, which calls into build file. So build fit just says it converts FASs to HEPs in Mac, or rather HEPs to FASs potentially. So like the Mark namespace within a desk is flat. It's not. It doesn't have any. Like every mark is just a term, just a pat-tas. So it's just a single atom. But you can define something at like FASMAR, FASFU, FASBAR, FASHoon, and that'll, instead of being FASFU, FASBAR as the name of the mark, the FAS will be converted into a HEP, and so you'll have foo hep bar will be the name of the mark. So that's just one atom, and kebab case. So all this stuff with fit, build fit, fit path, all fits, all that stuff, that's converting between HEPs and FASs, because whenever you go to import a mark from some other file, you import it with, or even when you refer to it to try to build it, you refer to it by this, A HEP, B HEP, C kind of name, but that might be at FASMAR, FAS a foo hep bar, or at FASMAR, FAS foo FASBAR. Either way, so we actually have to depend on all of those. And there's a precedence rule where the HEPs take precedence over FAS. All this stuff is actually pretty annoying, and I'm like, I've been wanting to rip it out for years and just not do this, but
yeah,
we
I
haven't
think
gotten
we
around
should
to
at
that.
some point. Maybe we
Yeah.
can do it during subscription reform if we want. Everyone's got to change their apps anyways.
That might be the right move. Just pile more stuff on top of that poor project.
Yeah, exactly.
The
Doing work is already. Might as well do more.
yeah. Well, it might actually be right though.
It might. I don't know. Yeah.
Yeah. And then, so in any case, we call build fit with the name of the mark, right? So because we've been asked to build a mark. So if we go back to build nav, right, we're just given the mark name. So we don't actually know which file path that's at. The file path might have HEPs or might have FASs in it. And so we delegate that to build fit. You say build fit, figure out which file it is. And it just builds it. It just runs a normal hoon build. So this file on the right here, this mark file, it is just a normal hoon file, like an or Ford file rather. And then we build it and we get this core, right? This bar cab core. So this initial step doesn't require any metaprogramming or anything weird. But then once we have this basic core, we convert that, we post-process it into a nave. We actually produce a vase of a nave because a nave is a parameterized type. So basically, a nave is this standard interface to a core that's parameterized on the type of the value and the type of the diff to that value. Right. So yeah, we see that nave here is a bar buck where type and diff are the type parameters, and then it's a core and it has a diff arm that takes that runs a diff between two different values, right? Old and new are both instances of this mark, and that produces a diff between them. Form is the name of the mark that we use for the diff, if I recall correctly.
Yeah.
So actually, this is referring to another mark definition here.
Right.
So
but
the diff of any mark has to itself be a mark. Yeah. So there is a mar text diff in addition to mar text. Join is a takes two diffs and combines those into one diff. Mashed is the same thing, but you know, with like more error information, basically.
Yeah, it's sort of guaranteed to work in a way that join is not. Well, guaranteed to work or crash, whereas join can just say these don't. You can't merge these as a conflict. I'm out.
Yeah, and all four of these, diff, form, join, and mash, those are all they're all revision control operations, basically. So if you want to
Yeah.
perform revision control, you know, diff patch merge, that kind of stuff, then you know that's done in a type directed manner. So each file type defines how those operations are performed. So that's what this naive is. That's what most of this naive is about. Pact is also part of this. So pact applies a diff to a value to get a new value. It's patch, right? Pact is patch. And then finally there's veil. And so this is a mold, actually, right? So this is a gate that takes in any noun and coerces it to a typed value. And so we'll see how. So in build naive, we're going to be constructing all of these arms. So we're going to be building a naive out of the core that we got. And so this is some metaprogramming. So we're going to do this in vase mode. And I just made a video about vase mode this weekend. So you might want to watch that for some background. But what we do is, so we start by line 637. Right, we've got our core, which is this just the vase of the core that we built, right? Basic build. And so then we want to run the grad arm against that core. Right, so we slap core lim faz send grad on 637. So what that does is that so we take a vase of our raw mark core, and then we fire its grad arm in vase mode, giving us the vase of the result. So that's gad. So if we look at text diff on the right here, when we fire the grad arm, we get this core with form arm and a diff arm and a packed arm, etc. But not all marks are like this, because the other thing that a mark could do here is to delegate all of its revision control operations. So the grad core defines all these revision control operations, and then not all cores actually do that. So if you pull up text diff, I think probably doesn't define them. Probably just delegates them.
That's kind of confusing, but like JavaScript.
Yeah, you can try this. Yeah. So MIME is a pretty common. A lot of marks delegate their revision control to MIME. Right. So here, instead of grad producing a core, grad is producing just a term, right? Just the name of just a mark, or just the name of some other mark. In order to figure out how to build this mark, like how to build the naive out of the raw core, the first thing that we do is switch on, is grad actually a core, or is it delegating to some other mark? So this is what the whatpat is in line 638. Whatpat q.gad. So that's saying, is the value of the result of running grad, is that an atom? If it's not an atom, it should be a core. But if it is an atom, then we assume it's a mark. So let's actually go to the no case of this whatpat, because it's a little simpler. In the yes case, we have to actually build the other mark first. So it's another case of recursion here. So let's assume that it doesn't delegate anywhere else. So if we do recurse, it'll eventually bottom out into this part of the code here. So there's this game leak stuff, which is some more dependency tracking, and it really starts on line 673. So 673, we're going to slap a bunch of stuff against slop of with face zoo step but. Okay, so So this is doing, there are two components here, right? So we're going to, so slap, remember, is run hoon against a subject vase. So first we construct the subject vase with slop, and then there's a literal hoon below that. So the zap com of tar hoon there says, take all the rest of this expression underneath me and quote it as an AST. So like compile it to an expression that actually produces an AST, a static AST. So all the rest of this arm here after that is, it's not getting run, it's being quoted.
Right. It's the same as this.
Yeah. It's calling the hoon parser on this and then producing that as a constant value.
Right.
Yep. Yeah. So we have this static hoon, but we're going to slap that against a somewhat dynamic subject, right? So that subject is slop of two vases, which just means cons the two vases together into a pair. So it so it takes a pair of vases and turns that into a vase with a pair. So the tail of that vase is Zeus.bud, which is the vase of the standard library. You might want to see bud, actually. It's at the top of the file. It's kind of nifty looking. Yeah, so what this is at the very top of Clay. And this is new, by the way. So bud is all of these different vases that are they're all evaluated at compile time. So on line 40, there's the ket sig. So as Clay gets built, it runs this whole expression. So we have this tuple of all these different vases that are used in different things, and we do this up top here to make sure that we don't accidentally copy any parts of Clay's state into its build results, which it turns out is easy to forget, easy to do if you're not careful. So Zeus.bud is just the standard library, right? So it's zapgar .zeus. And then all of these other things are expressions that were run against that that are used in different parts of Play. So let's go back to build nav. So let's see. Right. So we're going to construct a build subject for this quoted hoon. Right. And so the way we do that is we make a pair, and the tail of that pair is just Zeus, the standard library. The head of it is core, right? So core plus core with face takes a vase and slaps a face on it. So slaps the core face on the actual mark core that we built. And so then we have the subject that has the mark core in the head and the standard library in the tail. And the mark core is named core. It has a face on it. And so that way, whenever in this hoon that we slap against that subject, whenever you see core, like on line 675, that's referring to the actual built mark core. And from the perspective of this hoon here, that's statically typed, although for every mark, it's actually differently typed, right? So this is, because we're running it in vase mode, that's sort of how that works. So the first things we do are, we want to get to line 677 where we're actually producing a nav, and that nav is parameterized on its state type and its diff type, right? So kithep, nav clave, type, and diff. But we need to actually figure out what type and diff are, and so we can extract those from different parts of this core that we just built. So the type, which is the type of the mark state, is cab lusgal of core, right? So the lusgal of core is the sample, right? So it's tail is story, right? So it would be like a bunted version of that. So cab of that, right, underscore, is type of. So it's the type of the sample. So, story here. And then we do something similar for diff, where what we do is we take the diff arm in grad and we bunt it, right? So we just fire it with a default sample and it produces something, right? So in this case, it's going to produce a story diff. And so we say, take the type of running that. So it's the type of story diff. So it's going to be a story diff is the diff type. Right, so we extract, so we kind of, we do these little tricks here to sort of extract the type parameters based on just different parts of this core. And so then when we have the type parameters, we can cast this and say, okay, what's going to come out of this is a naive parameterized by type and diff. And so then we actually just have a bar sen line 678 that, like, here is the actual naive that comes out of this, right? So we're just code genning this, right? And the pattern is that you have this dynamic subject and you're running the static hoon against it. So you get a different thing that comes out, but in this case, we can actually express this as a static hoon. There are other parts of metaprogramming in Clay where we can't do this and we have to dynamically generate the hoon. But here we can do it statically, which is nice. So we generate a diff arm, which takes in old as type, new as type. Note that because we've extracted the types here, we can just write this in a nice statically typed looking way. So this actually just calls diff, right? It calls the diff arm in the grad core. Same with form. Join modifies the join in the grad core by wrapping in an extra layer of unit. It's an extra layer of null in the response. And so if A and B are the same, then it produces sig null. Right, so basically it's sort of hard coding that behavior so that because otherwise you'd have to write that in every mark definition to get this behavior, basically.
Right. If you want anything to be able to rely on this, and the merge code relies on this being true, then you need to guarantee it, which is what this guarantees. You can also, like, the join arm. No, yeah, sorry, yes. It's only considered right. It's only considered equal if they are exactly equal. Yeah.
Yeah, like you're not allowed to define your own kind of equivalence. You have to use noun equality.
Right. Exactly.
Yeah. Interesting sort of vague counter argument to wanting parametricity in your language. Right?
Yeah. I mean, if you really want something like equivalence that's not noun equality, what you would have to do is say, okay, the diff of these is an instance of your diff mark, which happens to get interpreted as a no-op or something like that, which could be a reasonable thing to do and is not going to break anything, but that's something different than them being actually equal.
Okay, I'm actually not familiar really with the part of the merge code that checks this, so we should make a note that when we go through that to revisit this and see like how this feature gets used.
Yeah, we'll get to merge at some point.
So join and mash are just little minor wrappers around whatever the implementations were, right, that do this extra check. Pact is a straight call into Pact in the grad core, and then veil, right, which is the operation that we're actually concerned with when running read file. Right, this is what actually gets called. Veil looks at noun pull grab. So the grab core is a bunch of arms. It's a core inside of the mark core, and each of its arms produces a mold, like a mold gate that can be used to coerce a value of that other mark into a value of this mark. So we're grabbing from the other marks. That's why this is grab. There's also the grow core next to grab, and so that has a bunch of arms that each look at the current sample and produce. So they grow our current sample to that other core. So we're either growing to or grabbing from. So this is saying, so the veil here is saying that the way that Clay reads from a mark definition to extract the way it extracts a mold that it can use to coerce like untrusted data is by looking at the noun arm on the grab core. So we're saying grab from noun. And so the veil arm actually just calls this, right? So it resolves to this. So then, so this veil here gives us a gate that we can call to coerce. And so that's how we coerce the page of data into a cage, is by running this veil here. So that's so now we've got our naive, at least in the basic case. And why don't we go through and look at the other case here, the whatpat of Q.GAD, so we can see what it looks like if it delegates its revision control machinery to another mark. So the first thing we do is we get mock, which is a mark, by zapgal and gad to mark. Right, so this is, remember, so gad was the result of running the grad arm. So we were just looking at the case where it's a core, but now we're switching to look at the other case where it's an atom. So if it's an atom, it should be a mark. So let's extract it to a mark. This zapgal is safe as long as the mark core itself didn't use a zapgal anywhere. That's sort of true of all of this. But the so in any case, we're taking this vase of a mark and extracting that to we're devasing it into a statically typed mark. So it's a PATIAS. This is the name of the other mark that we're delegating to. And so then here we get the delegate deg line 640 by calling ketbuck. So we recurse with max set to mock. So basically we call, so this is calling build naive. This is calling build naive on
on the mark that we're delegating to.
Yes. I don't remember why it's ketbuck. I guess there's, because we've got a bar dot in the line 630. Yeah.
Yeah. Yeah.
Right. Yeah. So we call build naive on the delegate, right? So that just recurses. That may itself have a delegate, but it'll eventually bottom out in something that that doesn't have a delegate. And there's a cycle checker in Ford that will actually catch that if that's not the case.
Right. Which we'll talk about later, but it's these two lines.
Yeah, that's what all the cycle.nub stuff is about, and all these functions. So once we have so now we have core and deg, right? So we have the basic cores for both of these things. And now we also need to build conversions in both directions. Because what we're going to need to do is whenever we get a value of, or at least for some of these operations, we're going to have to convert from the value type to the diff type, and then we're also going to have to convert from the diff type back to the value type. So tub and butt convert in both directions by building cast. kind of funny having to actually explain this. It's like, yeah, there's a lot of recursion here, jumping around.
Probably worth leaving off cast for the moment, other than to say that it is just going to be a function that looks kind of like this, except it's not actually on vases, I don't think.
Right. So the tube is the dynamically typed version of a cast, and the cast is a statically typed gate from one to another. So you can't really write
I mean, it's this, or not type diff. Mark 1, Mark 1, Mark 2.
Yep, Mac and Mach. Yep.
It's that.
That's right. Yeah, that's what a cast is.
So in the case of JavaScript and MIME, for example, it's a function from JavaScript, which is just stored as a pat, and MIME, which is stored as a MIME type, which is a path representing the MIME type plus the length in bytes and then an atom of the data. So it's just a function from the one of those to the other.
Yep.
And back.
And those casts they're built out of the grab and grow cores in these MIMEs. So
right.
Right.
So if you do delegate, then you need to be able to convert to them, right? So we delegate to MIME, which is okay because we have conversions to and from MIME.
That's right. So, all right. So now we've got all the stuff we need, right? We have our core, which is our actual mark core, our deg, which is our delegate mark core, and tub and butt that convert between them. And so now we can do this similar pattern where on line 648, where we slap some static hoon against the subject. Right. So our subject in this case includes all of these cores, right? Deg, tub, butt, and core, tagged with their faces each. So deg, tub, butt, and core. And also there's the other thing that we add to this subject is nave, the type of nave. Right, so nave here is a mold, or sorry, it's a type constructor.
Right.
Right, and so this was pulled from Zeus, right? It's defined in Zeus. It's defined in lull, which is part of Zeus.
Yeah.
And we need that so that in this hoon here we can cast the result to nave of type and diff. We could have just included all of Zeus there, but we don't need it. This is the only thing we pull from there.
Right.
So this is something very similar to the other case, right, where it extracts type and diff, except in this case it extracts the diff from the delegate.
Right. Compared to here, so type comes from the same place because type for JavaScript, is there, but but diff here, comes from the delegate core. It's also not the diff type. It's actually just the whole diff function because you don't need the diff type. Or no, sorry.
It's the diff type. So I don't know.
Yeah.
I don't know if
it's confusing, but yes.
I think that actually in 676 there we could probably just say diff grad core instead of cab tar diff grad core.
Yeah, I mean it's weird, right? Because we're pretending that the diff function is a mold, and then being like, but it's not, right? I would actually go the other way and say this.
I see. Yeah, maybe that's actually right.
Because technically it works.
It's guaranteed to be a mold where actually it might not be here, and in fact it's not.
It's not.
Right? That's not
right.
a mold because a mold would have to be able to take in any noun, and this can only take in a MIME.
Right.
Interesting. I think it doesn't really matter in this case because it's like the same spec that comes out, I think. Right, we're just using it as a spec, not as an actual coercion function.
We use it as a spec 3 times, but yeah.
Yes, but it's cleaner to do it the way you're describing it. It's safer.
Yeah.
So in any case, we have a native type diff, and so we're going to again build a core here, and again this is happening in vase mode. So diff here, this takes in the type of the core, old and new, which are both types of the core. Then we're going to diff them. We're just going to produce a diff that's based on the delegate. So we actually first what we do is we convert both values, old and new, into values of the diff type, and then we call the diff on the delegate between those. So we're sort of like lifting these old values to the delegate, not old values, lifting the values of the sort of underlying core into the delegate and then diffing them.
Right. So in this case, you have a bunch of you have a couple of JavaScript files, and you convert them both to MIME, do the diff there, and that's your diff. It's a diff that's defined on MIME.
Right. Yeah, it produces a MIME diff too, right? Like.
Right.
So so the rest of the arms here, form, join, and mash, just uses the delegate. Veil uses, Veil doesn't look at the delegate. That's the same, right? Because that does nothing to do with diffing. And then
Right.
packed is sort of both, right? So with packed, we have we're going to apply a diff to a value. And so the way that works is we use the delegates packed, right? Because the underlying core didn't define a packed, right? Like it just delegated. So we take our v, which is our value of the original mark, we convert it to a value of the diff type. We run packed there, which gives us a diff type, right, coming out. So we have to call but in the result to convert it back to the original mark.
Packed takes
gives a value of
diff.
The diff type. Yeah.
It gives a value of the delegated one,
right?
Not of the diff. Yeah.
Exactly.
Yeah. And so
sorry, I didn't say that very well, but yeah, it gives you a value of the delegated one, and so you have to convert that back into a value of the original one.
Right. Yeah, and notably these we can just delegate because, especially these two, like merging the way marks work is that merging goes from diffs to diffs, and so there isn't any value to
there's no reference to the original mark. Yeah, so we can just use those wholesale. Yep. All right, so here we are. That's it. That's how we get a nave.
Yeah.
So this was called from build dias.
Right. So that's these two,
which was
plus this you've done as well.
Yep. And and so to finish out how Veil works, right? Veil actually calls build dias, uses that. So the dias is a little vase wrapper around a nave. So notice that we don't. Yeah. So it starts really around 7:15, 7:14. So okay, we're going to produce a dias. Right, so dias looks just like the nave, except that instead of having type parameters, everything's a vase.
Right.
And so that way, like all the the sample is a vase, all the inputs and outputs are vases, and so that way the dias, this is just one type, and that you can use this for any mark, no matter what mark it is, they all have the same type. Unlike a nave where each mark is a different type parameter.
Right.
So they're different. They're useful in different contexts. But we build the dias out of the nave. It's just easier that way. Yep. So first we start with a subject, which has. So sorry, line 7 to 8, we actually build the nave.
Yeah.
All right. So we've already built the nave. That's nav, and then we stick that in our subject.
Right. So notably, this
should be backward. This is backward, I think.
Yeah. This is backwards, right?
Yeah. This should be the other way around.
I'm pretty sure this is safe, and about to do a bunch of testing anyways.
Yeah.
Yeah, because otherwise, if you did define a nav in there, it would be weird.
Then it would override. Yeah.
Yeah.
And we'd be very confused for a while.
Yeah.
Yeah.
It's also just going to be slow. I don't know, but anyways, yeah. But it's notable
before you find nav. Yeah.
Right. But like if you look at the difference between this and build nave, when we start doing this kind of stuff in build nave, we go into vase mode and we're like parsing stuff, and here we're not doing that. This is just code that accepts vases. It's not producing a vase. It's not slapping or anything like that. Not on the outside. It slaps inside.
Yeah, internally it does. Yeah.
Right. But that's why like this looks like this instead of being slapped with faces or whatever. It's done at a different level.
The outer call is not in vase mode.
Right.
And this core itself is not in vase mode. Some of its internal operations are in vase mode.
Right.
Yeah. So let's go into them actually. So we've got diff. And so what we need to do here is, we're going to take two values and take their diff, right? So the nav core has a diff arm, so we fire that's the lim diff, right? So in vase mode we fire that diff arm. So that's slap nav lim as diff. That gives us the diff gate, and then we call that diff gate in vase mode using slam. So we slam the gate on the pair of sample, which is the actual marked value that we have, and new, which is the other one, right? So we're diffing new against old. So Sam here is old, and new is new. Right. So so we're calling diff on this pair of old and new.
Yeah. So to be extra explicit, because like the word diff shows up here several times. This is the dias form of diff, which means it takes in one argument and gets the other argument out of its sample and so on. And so it takes in a vase, it produces a vase. This is calling in vase mode a nave, and so that's why it takes two arguments, right? Slop of Sam and new, because it's calling this diff, and that result is going to be of the diff type, from that type parameter,
right?
But since we're doing the whole thing in vase mode, it's actually going to be a vase of that diff type, which is exactly what we need to produce out of here.
That's right. Yeah, I forgot to mention that there is a difference between nave and dias. It's not just vases, but also that a nave is just a bar sen, right. And so you have to pass. If some arms there take in, a value of that mark, and some don't. Whereas with dias, it's a door, bar cab, and so you have to give it an instance of a, or it has an instance of the mark inside of it. So some things take two args in one and one arg in the other.
Right.
And that's because the difference there is historical, where the dias is like is older, basically, and that's how mark cores are designed. And then nave is newer, and I thought it would be cleaner to not have the core be sort of curried around its default, around its sample, because not all the operations actually look at that.
Yeah, if you want to carry it around anything, it should be just the grow sort of subcore when you're defining a mark. But even that
that would actually make a fair amount of sense. Yeah,
wouldn't show up here because we grow and grab end up as casts and tubes and whatever, so they don't show up here.
Right. Yeah, although as we rethink the mark system, making grow a door, I think actually might make a lot of sense.
Yeah, I think so.
Either that or a gate from a sample to a core, right?
Yeah.
To produce a bar sim.
Yeah.
Yeah. All right, so that's diff. Form just calls the form arm and then devases it with the zap gal to make sure it's a mark.
Right.
So that part of it's actually statically typed because the type there is always static. So we run in vase mode and then devase it.
Right.
So join. Let's see, what does this do? This we're taking two diffs, A and B. So if you look down a couple lines later, we swap A and B, so we make a pair. So that's going to be our arguments, and we slam a gate on those. And the gate that we slam is the join gate that we got from firing the join arm on our nave. So that's just a straight up vase mode call. But that produces a unit. And so we actually look at the value here, q.res, the value of the vase, and check if it's sig. So if it's sig or sig, then we produce that literally. Right. So we're basically, and then only if we actually have a value do we produce a vase of that value, right? So here what we're doing is we're taking a vase of a unit value and turning that into a unit vase of value.
Right. We're partially unwrapping it.
Yeah. Right. Right. So we're unwrapping the unit piece of it because that's the unit piece of it is always there, no matter what kind of data is in the vase. So in the first two cases, we just produce the sig or sig directly. Otherwise, tech. So sum of and then we run u.u here. So we extract the value, right? So in this line 727, we know, or like we assert that this actually is sig value, right? So what is cell sig tar, right? And then once we know that, then we can run u.u to extract the actual value. So the tail of the tail. And so we take that expression and we slap that in vase mode against this vase of a unit, and that gives us a vase of the actual value. And so then we prepend that with two sigs with tech, so that it's conforms to the unit.
Right. You could almost do this just as as slot res 7, right? Just say
you could. That would work. Although
I think you leave the face on it.
That's right. It would still have the two faces on it.
Or maybe one of them. I'm not sure.
Right. No.
Probably just one, but still, it's one too many. But yeah, surely there's a way to that if you call like repo on it, you probably could make it work. But yeah.
Yeah. The other thing you could do is you could call it need of need, right? So if you you could yeah. So you could probably slam it twice. Slam need, slam need.
Which at that point you might as well just do this.
I don't know. Slam need of res might be clearer, right? Like, let me write that out, see what it looks like. Be tech. I think it's just slam need, or it's actually slam zapguard need on slam zapguard need res. I think that's clearer, actually. Shorter too.
It's sort of clear, but it's also it's like heavier weight, right? It's got more indirections, whereas this is just like
there's more function calls, more phases. Yeah.
Okay, we assert that it's that it's got a couple of nulls because we just checked that, and we know statically this is a naive, and so we know it's producing unit. I don't know. I feel like this is probably cleaner than that.
Well, it's more it's probably slightly more performant, is what I'd say, like very slightly.
That's also true.
You're not sort of like jumping. You're not like jumping in and out of context and stuff.
Yeah, you're not making
too
many roads or anything. It's
well, this doesn't make any roads anyway, right? It just does dot tar. Like, it's just knock twos.
Slam doesn't make a road?
Nah.
Oh, nice.
Yeah, it's just a knock two. Doesn't need a road.
Okay.
Where we're going, we don't need roads.
Slam is not on the way to Rome.
All right, so this is what join does. So join basically just calls join, but then it extracts it extracts the unit from the result and sort of lifts that out of vase mode.
Right.
Mash basically that takes all these extra arguments, and so basically just constructs a more complex vase of all those arguments, right? So this whole slop of col slop and col slop, right? All that stuff is just, A is ship desk diff is vase, B is ship desk diff is vase. And so that's what we're doing in these lines here. Although this is also doing, these are all reversed, right? All the subjects here.
Yeah.
So instead of dot.zeus, this needs to be, or like it needs ship.a and then dot.zeus.
Although, then it's hep. Why even is there a dot.zeus? This is actually kind of confusing. Isn't it supposed? I feel like it's trying to say.
I think it's because but I think it's because you actually need the biblicals in scope in order to run Zapgar.
Oh, right.
Right. Yeah. Right. So you at least need. Yeah.
Need biblicals in scope, and so. Are we super confident that this isn't? Well, yeah. So it can't include anything other than Zeus, right? Okay. Then.
Right. The reason this
so
used to be
it really should go the other way then.
Ship.a, but the problem is that can actually include like a reference to the clay type. I think there's at least like not immediately clear that it doesn't. Whereas if we do it like this, then it does. Then it is clear.
Is it?
Right, that
like because ship.a, I mean it I think that's going to end up being just having references to the standard library, but it's not immediately obvious, like because this could be a flu or something, or like
I mean when the compiler is evaluating the type of something, I don't think it can reach outside of the subject.
Yeah, but the subject here is everything in clay, right? Like what is the type of ship.a?
But
like in this case, I think that's just gonna reference all the way back to ship, but if you had, for example,
but you might want to
ship,
cast it to
catch
pat
ship,
p, right? Yeah.
like now
If
your
you cast it
type
to pat p,
actually
right?
includes all this stuff. Cast to pat p probably works, yeah. That's not bad. Or else you just say, you know what, forget
Actually, probably the right thing to do
Zeus.
is because looking at this now, ship and desk, we know what those types are. It's send atom, send p, sig, send atom, send tas, sig.
Right. Right, just like that.
So that's probably the clean way to do it, actually, right? And then we don't have to reference Zeus. We don't have to call Zapgar.
Yeah, I think I like that better here.
Yeah, that's better. Nice and concrete, no funny business.
Right. As long as we don't change the type of desk or of ship, we make ship have a rift in it or something. But oh well.
We'll have plenty of problems if we do that.
Yep. I mean,
we need the diff there.
Oh, right. Okay. Because I was like, well, can we just maybe even do a literal slop here? Or, I don't know. There's 3 of them. I think slop is justified. Slop is very simple.
We just have to get rid of the close paren after desk.a.
Yeah. This is going to be virtually the same thing, right? Just B. Yeah. Yeah, I feel like that's better.
That's better.
Cool.
Yeah, that's what that should be. We really need to do this kind of walkthrough with all of our software. So
yeah. Like release notes?
What % of the lines we look at and be like, huh, that's not how that should look.
Yeah.
I mean, I would note though, since we started doing this with Clay, like what % of Clay has been rewritten? 20%, 30%.
By lines of code, it's at least 30%. Yeah.
Yeah. A lot more than had changed in the previous year too.
Yeah, well, Clay hasn't had a change this big since Ford Fusion, probably. Yeah, certainly.
Yeah, that was what, two years ago.
Yeah, we were getting close to at least 2 years ago.
Yeah. Okay. All right. So here's our res. I think this looks much more reasonable now. And we're going to call mash on it. And then it looks like we do the same sort of extraction, unit extraction, but just once, right? After that on q.res, this q.res sig, then sig, otherwise.
Sorry, where?
So the last 3 lines of mash, we're doing the same thing that we did in the last 4 lines of join, but it's just one layer.
Right.
We could write a little helper here. That's right. It's like unwrap unit, right? And then just call that twice and join. But
yeah, I like this very direct style.
But then, right. The problem with that is that then that code would be in the result of
right. You have this whole other core up here, and
which is okay, but
you can do it as an alias, or yeah.
Right. So then, then veil. And veil. Okay. Oh no, there's packed in between. Right. So packed. That's a very literal call that doesn't do anything interesting.
Yeah.
It just calls it in vase mode. And then veil is more clever, right? Because we have to somehow say we have to get the bunt to work, right? So you want to be able to bunt a mark, and we have syntax for bunting a mark in Dojo, the tar-pam mark syntax, and so that means that the veil gate here, you have to actually be able to bunt it. And I remember I was pretty pleased figuring out how to do it with this bar call here, and honestly, I do not remember.
Right. So the body of it is totally normal, right?
Yeah.
This is just call veil. Barcol is like a simpler version of bartiz. Basically, bartiz A is the same as barcol of cab A.
All right.
Or sorry, tar A. Yeah.
Or
right.
I would really do it the other way around, right? It's like
barcol is the simpler version of it, right?
That is that's right. Yeah.
Right. So when we think of what bartiz does, it's creating a gate, and a gate has a sample which is the bunt of its argument type. And so bartiz says, okay, give me a type and I'll go ahead and bunt it for you. And barcol is like, no, I'll just go ahead and give you the bunt directly. And if you need the type for whatever reason, which it does need to infer it somewhere, well, inferring a type from a value is actually the only way you ever get types in Hoon, so you can just do that.
Mm-hmm. And the type here is actually noun, it's tar. Right. Which it needs to be, right, because it's a mold. Right, but that's because we're doing a Bayes operation and extracting the Q, which is the value, which doesn't have any type information associated with it.
Right.
So it's just noun. And so we're taking nav and we're running tar veil. Right, so we're actually bunting veil, the veil of on nav there. Right, the nave. So we're bunting that. So this is like to preserve the bunted value. Yeah, so we actually call that here, and say, yeah, that's the default value in this veil gate. And so that way, if you bunt this veil, the wrapper veil, then noun is set to the bunt of the inner veil, and that way, when this runs, it'll be calling veil in Bayes mode on noun, right, or like this noun here. So it'll be validating the bunted value, which is going to work. Whereas otherwise, you just have the default noun here as the argument, and so if you bunted veil, the default noun is just 0, which might not be the default value for whatever type this mark is, right? If the type is a cell, for example, then 0 does not nest in a cell, and so if you try to validate it, then it'll fail and crash. So this is a way of sort of propagating the bunt of whatever mark it is through this Bayes interface.
Right.
Yeah. I was glad. I don't really remember writing it, but I do remember being glad it worked.
Yeah.
and glad that there was a way to do it. So, I remember I'd seen something crash and going, oh, that's not good.
Yeah, something needed. I can't remember what is going around bunting vase or cages or bunting marks, but something does.
I don't remember either. Yeah, something does it.
I think it might have been something used to do it before we had Nave. Maybe. I don't know.
I'm not sure.
Yeah, I don't
know. Is it used in the merge machinery anywhere? No.
It's possible that something uses it because it needs to call into Dias, and Dias requires a sample, even though it's not all the arguments need it. I don't know. Yeah,
Yeah,
I'm not sure where it gets used, or if it still does.
Yeah,
But
in
this
any
is
case,
clearly correct.
That is all of dias, build dias.
Yeah. Mm-hmm.
So let's go back to Mist and see how far we've gotten.
Right. So
we've done file, nav, and dias, and veil.
Right.
Except for describing how we convert from one mark to another, which are the next ones, cast and tube.
Right. Which was needed in one of these, but yeah.
Yeah, that was needed in build nav in case you delegate.
Right.
So I think we should go into that.
I'll start with tube. Or sorry, start with cast, right?
Build cast, yeah. And this produces a vase of a statically typed gate.
Right.
Yeah, so we're going to try to convert from A to B, right? We're going to produce a gate that converts from mark A to mark B.
Right.
So this really starts with 762 or 759, right? So first we try...
Well, 755, arguably.
Oh, you're right. Yeah, so there's a shortcut, a short circuit.
A base case.
If we're converting from mime to hoon.
Right.
Specifically that conversion.
Right, because how else, do you get from, from committing something as mime to being able to build it as a hoon file? That's exactly what you need. Everything else can be built off that.
Yep. Yeah, so then we hard code it to just say, we grab the data from the mime.
Right.
And that's our hoon value.
And we,
so
again, make a confusing vase out of it, but I think it's just Atom send T, right? Oh, no, it's a gate, right? So, yeah, I forgot it's a gate.
Right, yeah, so that gate needs to be, not have anything. It should not have any of the...
Right.
Yeah.
Not of, some forward cache in it or something.
Exactly, yeah, which it used to.
Right.
Like what's deployed on the network actually does have, like we have forward caches in it, in this gate. What's interesting though is you probably could like you could write a gate that just has sig, right? But that instead of Q, it's
just do like less
or it did
gal.
Yeah, I don't remember where it is in mine.
Something like that.
Yeah, something like that. Yeah, something like that. Instead of taking in less gal, it takes in tar.
Right. Sorry. Yes. Yeah. It's something like that.
Right. So that's the other way of doing this. We can refer to Zeus though. That's fine.
I think
everything refers to Zeus. So
yes.
This is. I think this is acceptable. Yeah. All right. So there's a short circuit. If we're getting in data from Unix, we need to convert mime to hoon, hard code it, get the answer. Yeah. Otherwise, grow arms of precedence over grab arms, right? So we try to grow, so mark A trying to grow to mark B takes precedence over mark B trying to grab from mark A.
I think they can go after the cycle checking, and it should because everywhere else does, and that's why your eye runs past it. All right. Yes.
Yeah. So, right. So first we look at grow, and then so let's look at the comments in this first before we look at the details. Right. So there's try grow first. So is there a grow core in A with an arm called B? Right. Can we grow to B? So we're gonna check whether there's that arm. Right. So line 768, we see grow core has an arm to grow to B, so we're going to use that. If not, then we try a direct grab, right? So that means we look at B, right? And if A has a grow arm, we don't even build B. Right? But if A doesn't have a grow arm, or like a B, so let's say we're converting from. Well, do you want to pick a pair, maybe with udon in it? Yeah, let's say we're converting from udon to mime, right? So we do have a mime arm in grow. So we're going to hit 768. Right, grow core has
garb isn't
has
real
a mime
anymore,
arm.
right? I can just delete garb.
That's right. Yeah.
Okay. Sorry. Go ahead.
Yeah. So we're checking like if we're trying to convert from udon to mime, then we say, okay, does udon first we build just the udon mark, right? Build fit there. Yeah. So that's old. We're going to convert from old to new. And so we check, does this mark in its grow core, does it have a mime arm? Which it does in this case. Right? And so because it has that arm, we can use that.
Right.
But if it didn't have it, then we actually go line 781, and we actually have to build the other mark.
Right.
And check whether that has a grab arm from udon, right? Like, can it grab? And so it looks at the grab core and then says, does that grab core have an udon on? Yeah.
Right.
And then, so those are the direct conversions. And then there's also, there are indirect conversions where you can delegate the conversion through some other mark. So if you look, let's try jump. Jump is one way to do that. I thought there was a second way, but maybe not.
There is. But it's mixed in with one of these, if I remember right. There's like a what pat or something.
Well, all right, let's go through it and we'll find it.
Because oops. Yeah. Because it's basically like grow could be no.
Is it that
grab can reference it? Right. Try direct grab. I don't know. Yeah, we'll see it probably if it is there. Maybe it's not.
Yeah, we'll see. Okay. So the first thing we do is we build the first mark. Oh, you want to see whether we use it anymore?
We don't. I was going to try to bring up an example, but we don't. Okay, that's fine.
Yeah. Yeah, so no marks actually use this, but they could. The idea is for specifying a whole path of conversions.
Right.
Which theoretically should be useful. But okay, so line 762, we start by building the A mark, right? The old mark. And we're going to check whether it has a grow arm. So first we run grow, right? Zapcom of tarhoon grow, right? So we slap that against the old core. And we have to mule that actually, because it might fail.
Right. Right. It might not have a grow core.
Right. And that's fine. It doesn't have a grow core. It just means that we have to pick a different option, right? So this is all in a big conditional here, where if that crashes because it doesn't have a grow arm, then we say no. But otherwise, okay, it does have a grow arm. Now so that produces a core, and so then slob checks whether whether the atom named by B is an arm in that core. So B here is the name of the second mark. So this is saying, is there a mime arm in this core? All right. So B there is this depends on which mark we're looking for.
Right.
So if that crashes, then we say no. Right. So we have to mule this too. Um, but then if it doesn't crash, then and I think slob can crash if grow is actually not a core, right? If it's something else.
That sounds right.
I think slob will crash. I'm not sure about that.
Something like that. Because otherwise it produces a Lubian.
Yeah. Right. So if it produces Lubian, then return that Lubian, right? So slob will say yes if that arm is present, and otherwise it'll say no. So if the arm is present, then we do some dependency management stuff and jump to 774. And so we just slap some dynamically generated hoon against the old core, which we call core here. So note that we can't just zapcom this whole thing.
Right, because if we tried to, then we do.
Well, we just can't because this refers to B.
Right. What we want to do is B, but we actually want like Lisp style unquotey or something if you want to do it there.
Yeah. Right.
That's what
I
you have to
do.
But we don't have. That's not a real thing. It's,
right. Yeah.
Unquote.
Yeah, we don't have that sort of. I'm sure there's some Lisp thing that this corresponds to, right? Yeah.
Quasi-quoting. Yeah.
Oh yeah, it's is it unquote? No, it's called. It's like in the Lisp macro syntax, right? There's quote, and then there's this other thing, and it's the other thing that we need. I don't remember what it is. Quasi quote.
Yeah, that's the one. Because quasi quote then lets you unquote.
Yeah, and it's a backtick. Yeah.
Right.
As opposed to a front or just like a single quote. Unless, yeah.
Right. Yep.
Okay. In any case, Hoon doesn't let you do this, and it might be good that it doesn't.
Maybe I don't know. Like quasi quoting is nice and it's maybe worth putting at some point, but it shows up pretty rarely.
Yeah, this is one of the very, very few parts of the kernel where we do anything like this. Maybe the only one. I guess the compiler does some things like this, but yeah. But it's not. The other thing is it's just not hard to do. It's like slightly. It looks a little ugly, but once you're used to it, it's not bad. Yeah. So anyway, we make a bar call, and right. So a bunch of the leaves of this are actually static hoons, right? So we have a zapcom of V is lescal.core, right? So it's a bar call, not a bar tis, right? So we're taking the actual value, right? The default value from the core, and we're making that the default value of our gate, right? So we're producing a conversion gate from old to new, right? And then we're and then we're tisgaling unquote of B or quasi quote of B, right? Because so B here is just like send mime, right?
Actually, it's not some mime. It's just,
just mime.
It's the lim mime.
It's that.
Right.
Yep. And then of grow core B. Right. Yeah. So that's what this always looks like. It's just it'll instead of mime it'll be some other thing.
Right. Which is basically the same as this, if that's clear to read. It's like basically it's a function. Whose argument is the type of
the sample of
core, which where do we get core from? It's old, right? So it's this. It's from that, and what it produces is the result of mime.
Yeah. Totally. Also note that we just call build fit here. Like we don't like you can generate conversion gates without actually having to generate naives and marks. naves and diases. Right. So we're just building the file. We're not
Yeah.
actually
Yes.
like,
That's true. Right.
yeah.
Right. I mean,
Which is
and
it's
that's in
just
part
nice because it doesn't.
because like naves and diases don't have grow or grab
Right. So they're really like kind of
things. Yeah.
two. This is I don't know, the interface segregation principle, right? The I and solid. Um, but, it's the one that nobody ever remembers, right? But the it's right. They're like, not to say that we've implemented it correctly here, but that there really are kind of two different parts of the Mark interface. One is all the grad stuff, and the other is all the grow and grab stuff. And there's a little bit of overlap in the sense that grab from noun is used to build veil, but and arguably it shouldn't. I'm not convinced that that's the right way to do it. I think it would be a little bit cleaner to have like a veil arm on your core. It's such a fundamental operation.
Yeah. There's an argument to be made that there's really three things, right? A dias or a nave is that's all the stuff that comes from grad, and then you have a bunch of different casts and tubes, and then you have veil, which is like the mark as a type.
Yeah. Right. Yep. I think that's conceptually pretty clean.
Yeah.
Yeah, there are the three different things you can do with marks. You can validate it, which is basically just treating it as a type. You can do version control stuff on it with grad, and you can convert it to and from other types with grow and grab.
Yeah. Yep.
Yeah. So this is how we make the gate if we have a grow on. Right. We code gen a little bit of hoon. It's almost static, except that we have to dynamically pick which arm to call, and so we can't quite zap comment.
Right. Yep.
So if that doesn't work, though, right? If for whatever reason we don't have a grow on, then we have to build the other mark and try to grab from that. So first we build new, right? So we have old and new. These are both just raw mark cores. So then we do something very similar here, where we try to fire the grab arm, which should produce a core, and then try to fire an arm named after the old mark A
right.
after that.
We probably could have done that here too. Be cleaner to read.
I'm not sure if we can, but it does sort of seem like you should be able to. Yeah.
Oh, I have a vague recollection that it ends up being a mess because in fact, I'm not even sure that it works correctly here, but it ends up being a mess because like, suppose you don't have a mime, and then you try and fire it. Well, it's going to get mime because mime is defined in the standard library as the type, and it'll flow through it unless you put in enough ket whats or whatever. Which is not ideal.
Which could be a problem here too, right?
It could be. Yeah, but it looks nice and simple.
Yeah. Okay. So well, then we check it, right? So so we see is first. So so we do an and here of did this succeed, and then also is the value of the result a cell? What's that about? Is that
that's the one that's trying to let you also say, actually, to get to mime, I want to go via
That's right.
send-txt or something, right?
Yep, and that shows up again in line 794. So we actually do check for this.
Oh,
Yeah,
okay.
so there's jump.
Okay, good. Yes.
And there's also grab indirectly.
Right.
Yeah. Okay, cool. Yeah, so anyway, we get this stuff. So now we have our what is hopefully a grab from MIME arm, grab from udon or whatever.
In which case, that's it.
Yeah, right. We just we use that. That's a gate. It's the phase of a gate, and so we just produce that.
Yep.
Right. Otherwise, we check if there's a jump arm, jump to whatever, and if so, that jump arm should resolve to a mark name. And so in that case, we'll compose the cast.
So this would be like, I want to convert to MIME via send-txt. Would look like this. Yeah. This one is, I want to convert from MIME. So like if you were converting the other direction.
Yeah.
But I only have one file open.
Right. And the reason we need a separate jump arm, you can't just say grow.
It's right? Because this
why don't I just say grow, MIME, produce, send, whatever. It's like, well, because it just runs it and gets it like a value, right? Like,
right.
It can't distinguish between, right? Whereas with grab, we can tell, like, okay, is this, if it's a cell, then it's got to be a gate. Otherwise, it's an atom, so it's a mark. But we can't do that with grow because it might be growing to an atom.
Right. Right. Like if it's converting to jam, it's going to be, likely that, and that's an atom. Right.
Yeah. Convert to text. Or I guess text is a pain,
but text is not. But
convert to hoon.
Convert to hoon. Yeah.
Yeah.
Convert to JS. Yeah. Many of those are.
Yeah, a bunch of examples.
Convert to udon. Yeah.
Right. So it's either take every arm and grow and make it produce an each.
Right.
Or it seems a lot cleaner to just have it be a separate core.
Right.
A jump
or
core.
you could uncurry the sample, but maybe you want this to be bar cab here, in which case you run into the same problem. Or I don't know. Yeah. Yeah. There's a few options, but this works fine.
Mm-hmm. Yep. So compose casts. That takes two gates and makes a gate that calls one and then calls the other.
Yeah.
On the result.
Yeah, it's just called build cast, and then we use Cork instead of just doing it ourselves. But sure.
Yeah. Yeah. So Cork is Hoon's compose functions. That's also backward.
Yeah. But also shouldn't be there, right? This should just be.
What?
Oh, no. We don't have enough types to do it that way. Yeah, okay. We do kind of need Cork or something like it.
Yeah.
Like it.
I mean, you could easily.
You could do it this way, right? It's that, right?
Sure. Then it's wet though, which is.
I mean, Cork is producing a wet thing, anyways. But I don't. Yeah.
That's interesting. Actually, it'd be better not to. So it would be better to hard code it as not wet. It doesn't need to be.
Do we have the type?
But.
I guess it's cab.
We could probably get it. It seems like it's kind of a fair amount of work.
It's that, right?
Yeah. Yeah.
That might work.
Actually. Yeah, it might.
Uno and dos go in that order, right? go from X to Y. So this is X to Y and then Y to Z.
I think
No,
you
I
want to
think
call
it's
it
backwards.
dos and then uno.
Yeah. And because it's definitely taking
And this is
the argument
uno,
uno, which is X.
Right.
Yeah. Yeah. I don't know. I kind of like that better. If it blows up, I'll probably just revert it. But I think that's going to work.
Yeah, I like it too.
And now it's not wet.
Yeah, it's nicer. It's more like, more direct.
It's actually very
less reliant on.
In various cases, it's probably nice that it's not wet anymore. But yeah.
Yeah. Yeah, I mean, anytime we can have something be dry instead of wet, probably should.
Yep. Water is the enemy.
They put fluoride in it too.
Exactly.
Yeah. So compose cast is what happens if you indirect through some third mark.
Right.
And then there's another case here near the end. It's easy to miss where we check if we're converting anything to noun.
Right.
So if there wasn't something specific and we're converting to noun, then we just call the same function. Right. So basically, because anything's a valid noun. So even if nothing specifies how to get to noun, Play will generate something to noun for you, and it just produces the value.
Right. Right. And if none of that, then we crash.
Right. So if none of those work, you're screwed.
Yep.
And if a forward build crashes, like while you're trying to build a desk, then that will cancel the commit.
Right.
Right. So if you're so that will revert, or not revert, but the commit will fail and will not be applied. Mm-hmm. There are other builds you can also run builds later after you've done the commit, and that doesn't revert the commit. It's just that particular build will fail.
Right.
All right, so now that's build cast. So build tube is a dynamically typed wrapper around that, and it's going to look very similar to the dynamically typed wrapper around marks, but it's simpler.
Which build dias.
Yeah.
But yeah,
so
simpler.
This just builds a gate that. Okay, so we call build cast. So now we have a vase of a gate, and then we just say slam that gate on a vase. This would also be, the other way around. Although I think in this case it doesn't actually matter really, because the other thing has a. Well, I guess if Zeus had a gat, if Zeus had gat inside of it, then it would matter. Yeah. So this is better.
Yeah. So this is then. Right. So this is producing, and let me get this back to where it's supposed to be. This one's producing a tube, which is a function from vase to vase. So vase of the first mark, vase of the second mark, and so it's producing an actual function, which is why we can't, do any of those tricks where we like try to make it more. More literal or put in a type or whatever. No, we're actually producing a function, and so we want that function. It needs to be able to refer to slam at least, and in particular, that function needs to not have any of our own context in it. So we use the tisgar like that.
Right. Yep, that's right.
Yep.
All right, so let's go back to pour, because I think we've actually gone through. Missed. Yeah, we've gone through most of these.
We've gone through all these except arch.
Yeah. So, and there is another part of for that we haven't really gone through, which is, how do we actually get a pile, or how do we run a pile? All right.
Right. So
like, what are the different kinds of builds? What different kinds of imports you can perform?
Yeah. Okay. So I have a meeting in about 35 minutes. Just FYI.
Okay. So I think we should maybe just do a very brief description of the kinds of imports you can do, which is documented in Pile, actually. Yeah, so we can just look through these really quickly.
Yeah.
Right, so you can import something from faz-sir, and yeah, run tots is a good thing to look at here, or run Pile, I guess. But yeah, run tots. Yeah, so run.
I don't know where it is. Run prelude, I guess. But yeah.
Okay. Yeah. So first, we look at all these different things and run them in order, right? All the different things, all the different kinds of imports. You can do, any number of them in a row. They do have to be in this order. And then, and once you have, so then it just runs it. So sir and lib, so fazhap and fazlus, those work the same way. You're just straight up building a file from the sir directory or the lib directory. There are structure files, which are like header files, lib or library files, which are just imports. But they're both the same kind of import. It's just a convention about whether you put it in lib or sir. And it uses the build fit thing. So you can import it with sir hep file, but that might actually be in sir faz file, just like Mark's.
Right.
All right, so that's the first two, and so it calls build fit, and then depending on there are a couple different versions of the syntax where it may have a face on it or not, and so if you just do fazhap sir file, then it sticks the sir file face on there, and you could also do fazhap foo tis sir file, and that'll put a foo face instead. Right. Or you could do fazhap tar sir file, and that puts no face on it. And so that exposes all of the different, that's like a, unqualified import. Qualified import. Or, import tar from whatever, right, in Python.
Right, which by the time we're done parsing it, those three cases have been reduced to a unit term.
Right. Yeah, and that term might be the same as the actual file path.
Right, often is.
Yeah. And so in run tots, we call build fit, and then we take the result and pita. So we get pin, which is a vase. So we say, if we have a face that we're supposed to pin on this thing, then wrap the type in send face with that face. So we change the type to include the face, right. So that when it gets included in the subject, which we do in the next line, we replace sut with slop, pin and sut. Right, so that's our build subject. So we're prepending the result of building this sir file into our build subject, and that result may or may not have a face on it. So sir and lib work the same way, and then faz-tis just imports a hoon file, like builds and imports a hoon file from anywhere else. So anything that's not sir or lib, actually it could be sir or lib, but you have to put in the whole path. So it's just sort of a non-shortcut way to do it. And I'm very tempted to remove fazhap and fazlus and just give you the faz-tis version.
Yeah.
And say like, you always have to put a face on it. Sorry. Like,
right.
You can still.
That's a clean way to
later if you want.
Remove a lot of the instances of fits. Still have marks then, but yeah.
Right. That's right. Yeah. And that's one of the big reasons I'd like to do that. Yeah. So then there's faz-sig is the only thing that uses arch actually. So then what that does is you say I want to take all of the hoon files in fazpath or whatever that directory is, and build every single one of them. Or it has to be directly under that directory, so it can't be like fazfoo, fazbar, fazbaz, or whatever. Just fazpath, faz something, fazhoon.
Right.
But it takes all those files, builds them all, and then checks that the result nests in a mold that you specify in your fazsig. Right, fazsig face type that, and it's a spec in run ras. So so it runs a nest check. to make sure that the all of those files nest in the same type, and then produces a map. So the negative map from the file name to some typed library, typically, or plugin. This is really for like plugin systems. Powerful and FastLab has some apps that use those.
Yeah, I think Gora uses it too. Yeah.
Does it? Okay, interesting.
I just noticed because I broke it and then when I was trying out those apps, I was like, oh, okay.
Nice. Yep. So that's fazsig. Fazsen imports a mark definition, and I don't remember if that's a dias or a nave. Looks like a nave.
I think that's always gonna be a nave.
Right, and it can be a nave because you specify which mark it is.
Right.
And so then you can get a statically typed value out of that, right? So build nave produces the vase of a nave, but then that's just slopped into the subject in vase mode, so it becomes a statically typed core.
Right.
So that's pretty cool, right? You can just import. So you can get Clay to build a Clay file to build a mark definition for you, that resolves all these references and all this crap, produces this parameterized core, core with type parameters, and then you can just import that into your subject, and so now it's this statically typed thing that you can just access really easily. And you can do the same with fazbuck for converter gates, right? So you say fazbuck, some cast from mark to mark, statically typed gate that you can call to convert. And finally, there's faztar, which might be run bar. That's run bar. And so that just imports files. So it validates the files. It imports a file, right? So you give it you give it a path, and you actually give it a mark that you want to receive it as, which might be as a different mark from the file name. So it'll convert it if needed, and then it slaps the paste on it and sticks it in your subject again as a statically typed datum. So this is like if you have some sort of static file that you want to use as part of your build, right? Sometimes you need to distribute just like data with your application. So you can import that as typed data, and you can even convert it from something to some more convenient format when you import it.
Right.
So these are, that's what you can do with Fort.
Yeah.
Maybe we should go through the dependency tracking stuff in a later session. You gotta go.
Well, let's see. So I have 25 minutes, which might be just enough if there's nothing else to cover. Let's see if there's anything else to cover. Read file, build nave, dias, cast, tube. We covered virtually all this. Go ahead.
Prelude. I think Prelude is the only thing we haven't covered.
Which is run parse file, and then run prelude, and that's it. It's the same as build file, except don't do the last step. In fact, build file now, build
dependency calls run prelude.
Yeah.
Oh, run prelude.
This also calls run prelude. This is just for the language server. It's a typeless, like throws away the cache, just something that you can scry out. It's pretty hacky.
Yeah.
Probably shouldn't exist.
Right. Yeah. So it's specifically so that we can support the language server protocol, in doing so that an editor can call into Urbit to ask about like metadata about some source code.
Right. Yeah. Then that's it. Unless we want to actually look at the parsers, but the parsers just parse this. And so I think we might have time to get into the caches some.
All right, let's do it.
So if we look back at the args, there's a couple caches here. We'll look at the main one first, which is flow, this is a global cache that is from from a description of a build, and it needs to be a fully complete description of a build, because we're going to call this from different desks, different versions, different everything. So it's got to have not only the file, the path, but also the contents of the file and the contents of all the dependencies that it has. It needs to be part of this cache key. And then the result is going to be whatever the result is. So in the, which to expect, right? It's either going to be, in a lot of cases, it's a vase. Read file is going to give you a cage. Dias is going to give you a dias. Tube is going to give you a tube. But that's just like the result of building it. So the thing to try to understand then is leak, which is this cache key, which is two things. So we talked about mist a bunch. Pour is the same thing, except each of these, they kind of all tend to depend on each other, except veil and arch, which only depend on the actual contents of it. So if the veil of a file, so the read file of that file, only depends on what's in the file. It can't depend on anything else. I'm not sure that's 100% true. It can depend on marks used to convert it, but
it might not, right? It might just be this,
right? It might not,
and it at least depends on the lobe of this actual file,
right? Exactly,
like the hash of the contents,
right? Yeah. And if it's a directory, we just put the whole directory in there. The goal being that if you call veil with path and a lobe from two different desks, for example, it shouldn't you should be able to share that cache, because it's going to veil to the same thing as long as you have the same marks. So we'll specify its marks as dependencies, but if it doesn't have dependencies, for example, if it's a hoon file or something, then that's all the information you need. Or if it has the same dependencies and those dependencies match, then you're good. And any of that. So this is just like a more complete description of what's in there. But that means, for example, if you're doing the dias, right? That's a dias is always going to depend on the veil of that mark. You're never going to have a dias that doesn't have any dependencies, because the mark name is not enough. It depends on the mark file. And in fact, it'll go via file.
Yeah, so
dias will depend on file, which will depend on veil. Go ahead.
So only veil and arch can be leaf builds. The other ones cannot be leaf builds, and not all veils are leaf builds. But
correct.
But any leaf build is either a veil or an arch.
Yes, exactly. And so a leak then is just one of those, which is a fully specified forward build, and the dependencies that it has. And these are the direct dependencies, but each of the dependencies is itself a leak, and so that might have its own dependencies, and it creates this tree structure.
Yeah, and note that these dependencies are they're established as the build runs.
Right.
Then it notes what it actually ended up depending on.
Right.
Or could have depended on. Right.
Yeah, it does specifically anything that it did try to build. So anytime that you end up in we needed to do build dias showed up here, that's going to add itself to the dependency list. Anytime you call build something, it's going to add itself to the dependency list.
Yep.
Okay, so our cache is from that cache key to the result, and we also keep a reference count. And that reference count is going to be is the number of desks, or is so a reference there is either because it's something else in the cache refers to it. So for example, a dias is going to depend on the file that defines that mark. And so both of those are going to be in the cache, and the reference count for the file is going to be at least 1 because the dias itself refers to. The other place those references can come from is each desk. If a build is valid for a particular desk, then it'll have a reference, like it'll have sort of a root-ish kind of thing in there, and so it'll have a reference. And then the way that we end up clearing this cache is if it becomes invalid on a desk, then we'll decrement that reference count. And if you decrement the reference count to 0, then we'll throw it away from the cache. We'll ignore that for the moment, and understand how this works as a cache itself. Refs only exists as a way to save memory by throwing away the cache somewhat aggressively. So, if we look at something like build dependency, or even read file, because that one's, sometimes a leaf, right? It calls a few things. This is that preamble that we've been ignoring. The main things are, so the main ones, let's see. So gain leak is most of the guts of this and is longer than I remembered. Let me think, what's the right way to think about this? Okay, so we take in a build name. So we say this is the build that we're trying to build. And we want to, and we take in a trap of something that says, okay, if you don't find it, then this is how you would build it. But if it's in our cache already, then we're not going to call that.
Okay. It's not really a trap. It's a function of the current forward state, right?
Oh, sorry. Yes. Right. Because we might modify the state ourselves.
Yeah.
Struggling a little bit to think about like how to, because this whole thing is also a little bit circular. But the state that this ends up using, and that we should make sure we understand a little bit of, is there's this concept of a stack. And a stack here is if I'm in the middle of building something, so I'm in the middle of reading a file, for example, then at the beginning of any of these, part of the preamble is you cons an empty list onto the stack, and that's all the dependencies for what you're doing right now. And then as you call things, we're going to add ourselves to that stack, which ends up happening here. And so by the time you get to gain leak, because gain leak you call once you've built all your dependencies, and you now want to actually produce the result.
Well, it wraps the function that runs the build and may gather dependencies, right? And so,
well, actually, no. So it's not supposed to, but notably, but it does here, right? Technically, this should be here. I'm a little bit worried about that, because what that means is that as written, it doesn't depend on the mark definition. Okay, I need to think about that more closely. But if you look at like build nav, for example.
Yeah, it doesn't happen too often. You might want to test it with like reading from a mine file or something. Or actually not mine, because we hard code parts of that. Right?
Yeah. So this is the way gain leak is supposed to be used, is once you've built all your dependencies and now you're about to produce the actual thing, that's when you call gain leak.
Okay.
And so we pop off the stack all the dependencies that have accumulated by calling like buildcast and whatever. And we make a leak. We make our cache key by saying, okay, let's get our build and the dependencies that we in fact needed. And that's going to be our cache key. Ignore the cycle checking for now. And we say, okay, that's us. So this was all the dependencies that we had. So now we're going to put that into our callers dependencies, right? We're going to put ourselves into our callers dependencies.
Yeah.
Because obviously our caller depended on us. And that's how we got all of our dependencies. And so that's how you maintain the stack. And that's like actually the entirety of it. Other than, we can ignore Sprig. Other than that, you just got to remember every time that you enter one of these functions, you need to push on an empty list on the stack, because now you're getting your own dependencies. Okay. So that gives us a cache key, because we now know what all of our dependencies are recursively. And then we can look that up in the cache. And if we find it in the cache, then we go ahead and return it. And we also maybe increment the ref count if this is the first time that we've referenced it from this desk, which is what Spilt is keeping track of.
And it says add there, but Spilt, but refs is only ever 1 or 0 or 1, right? So like,
right.
I kind of feel like we don't even need considering that you're converting it to 0, 1. I don't think we even need the check there.
Yeah, you're right.
It's like we could just add it.
So if it's Spilt, then 0. That means. Oh, I see what you're saying. Well, yeah. So. Right, it's just increment of this, but also this can be defined in terms of Spilt, and then it gets simpler.
Yep.
Although
I think
the printfs are nice.
It's simpler too.
Mm-hmm.
But you could move the tisfaz refs into the printfs.
Yeah. Right. Kind of surprised Shift J worked there, but it did.
Add one. I think you did. I think you need to indent it one more space.
Oh, you're right. So this is
just Spilt.
Right. Not Spilt.
Not Spilt. Yeah.
Right, because that means it hasn't been referenced on our desk already. Then we want to go ahead and bump the ref count. Yeah.
Spilt, not split.
Right. Yes. Right. So if we found it, we might still have to write to the cache if it's the first time on this desk. In which case, yeah, go ahead and do that. Otherwise, but in general, you just refer to it, and that's pretty fast.
So remind me again. Spill rather.
Right. Spill. I was hoping to avoid, but I don't think we can.
Oh, okay.
All right. So spill is per desk. So flow is the global cache. Flu is the per desk cache. And so spill is the set of cache keys that we reference from this desk. Okay. And so we check and see if we've referenced this before in order to do that. If we have not referenced it, then we're going to go ahead and put it in spill, as well as, of course, incrementing refs. Should this? Yeah. This one is also counting the same reference. Anyways, yeah. So if we didn't find it, then we want to call next, which is that function that was passed in with our current forward cache, because we've modified or forward state because we modified the stack.
Where is it called next? Okay, good.
Right here. Yeah. And next produces a soak, which is the forward result. And so we just put that in the cache. We give it a ref count of 1. That reference being this thing in the spill.
So we're sort of like assuming that we didn't already have it in cache. I guess we knew we didn't have it in cache because otherwise we would be. Yeah. Okay.
Yeah. Right.
That makes sense.
And then we also go through and say, okay, all of our dependencies, since we just added something to the cache that refers to them, we're going to go through and bump each of their ref counts. So, yeah, that's pretty standard.
We bump the dependencies ref counts too, but just the top level ones, right? Not
just top level ones. Yes.
Yeah. Yeah. Okay.
Yes. And so that gives us a result, like a forward result. And so if we've seen this from this desk already, then we're done. Otherwise, we need to go ahead and put it in the set of leaks.
Actually, so remind me, why is it that why do we also add ref counts to the dependencies? Because isn't it already pinned by line 1215 where we put by cache.nub leak and soak?
Well, this is for us. It puts it in, but our dependencies now have another reference, and it might be that that there was something already in our cache, and be because of some other desk. That other desk invalidates it, and so it wants to free that, except we still refer to it. And so we have to keep track of there's still someone else that refers to it, which is us.
Oh, I see. So basically, like when this leak is created, like until we run this loop over deps, like they may not have any ref count at all. Like ref count might be 0, but it actually it's effectively like this top level leak that has a reference to all of its immediate dependencies.
Right.
And so those need, okay. And I guess this is happening sort of at every level. So this never jumps 2 levels, and so
right.
At every level, all of the deps have at least one ref on them.
Yes.
Okay.
Yes.
All right, that makes more sense. Yeah.
Yeah. Okay, so that's all of gain leak, which it's confusing to think about how that does everything, but then the key is just to call it everywhere.
Yeah, I mean it is not the easiest thing to understand.
Right. The other thing that's in here is next to the spill we have a per desk sprig cache, which is virtually the same thing as the global one, except you don't have to generate a whole leak. You can do it from the mist, because the mist is per desk and per revision of desk, right? And so we use this because it's much faster to generate a mist than a leak, because a leak has to find all its dependencies, and then to find the dependencies, you're potentially building files and you're doing Vase operations on them. You're running the compiler in general, which is potentially slow, whereas this is going to be instantaneous. And
this is the lack of that cache was one of the major reasons that the lack of the sprig caches, or we didn't have that idea back 3 or 4 years ago when I was working on Ford, and I was thinking, that leak data structure, I've been thinking about that for a long time, but I couldn't figure out how you could do a quick cache lookup based on that, right? Because just that, it's okay, if I knew exactly what dependencies this thing had, then I could just look it up in the cache and run it. And in order to have a global cache, you need to know all of the dependencies.
Right. But a local cache can do it by
because otherwise
name.
it can't be. What?
But a local cache can do it by name, basically.
Right. And so, so if you try to do it with just the global cache, it ends up with this very slow lookup where you just have to regenerate all the dependencies and do this like complicated recursive process. But per desk, you actually know what these things were, right? And so, you can just check very quickly, like, can I use the same version as last time?
Right. Yeah. Like caching wise, the primary innovation of Ford Fusion was this cache that you can just look it up by name, basically. And we gave up some stuff that old versions of Ford had, which was something more like this. And so the caching work that I did recently was basically realizing that you could have both.
Yeah.
And that that it's worth having both for a variety of reasons.
I mean, I will say that this design that we have now, I think, is I think is like the outline of a really good answer to the static versus dynamic linking question. And as far as I'm aware, this is like the best answer that's been come up with, actually, because these builds are nominally static linking, right? We're copying pointers too, but we're copying the all the libraries into the subject, right, and into the final program, right? It's like recursive copying procedure,
right?
So that's very much a static linking sort of thing, right? It's not like you build it and then at runtime you somehow like inject some other core or something like that, right?
No.
Which would be more like a dynamic linking. But the reason people often do dynamic linking is that you often have duplication of builds, right? You often have duplication of some library between a bunch of different applications, right? You might have like OpenSSL or libc, and you have 100 different apps running on your computer that share that library. And so if you have a different copy of that library in memory for every program that runs, it actually gets pretty big.
Right.
Even today, with as much memory as computers still have. So people end up doing dynamic linking, but then dynamic linking is just horrible in so many ways, right? Like, you end up with DLL hell. And,
right.
And so, you really want static linking if you can, but with this, we have static linking, but global deduplication of every library and every kind of build and so, it's like you wouldn't really gain anything from the dynamic linking, or like this does the good part of dynamic linking, but you keep the tight spec of a static linker. And so I think it's like, this is just how it should work, basically. We can basically put that question to rest.
Yeah. Okay, in the next couple minutes, I think we can cover really basically the last part of this, which is, so we looked at gain leak is how you add things to it. So gain sprig that shows up everywhere is just check if it's in our sprig cache. If it is, return it, and put the right put us in the dependency stack, and that's it. The way you actually add things to sprig is this other line here at the bottom of gain leak. If we haven't seen it on this desk before, then we need to add it to spill and sprig. So spill and sprig are going to have the same. They're gonna have the same size, right? They're referring to the same things. And then lose leak is just a very classic. How do you get rid of how do you lose a reference in a ref counting system? Well, check and see if it's there. If it's not there, then you're freeing something that's already freed, so you have to free somewhere. Otherwise, if it has more than one reference, then we go ahead and just decrement the reference. If it has 0 references, then again you must have to use after free. If it had one and now had 0, and now has 0, then we go ahead and free it, which means delete it from the cache and go through all of our immediate dependencies and recurse. and that's it.
Yep. This one's very straightforward. Yeah.
Right. Lose leaks is do the same thing, but on a whole set of leaks. And then the place this is called is promote forward, which we'll look at when we actually do the commit flow. But it basically says, okay, go through your set of leaks. It's very fast to look at a leak and know what files it depends on. You just recurse through it and say, does it depend on this one? What about that one? And so we give it a set of paths that changed in this commit. We go through those leaks. Any of them that are invalid, so if they're not invalid, then we put them in the new spill. If they are invalid, then somewhere we lose. Oh yeah, so promote forward produces a new cache, and then we say, okay, anything that was in the old one but is not in the new one. So take just the differences of the spills. If it was in the old one, but not in the new one, then go ahead and lose it. And that's it.
Yeah. Nice.
You had to be a little careful with keeping track of when to call the various functions, but the preamble's not too bad. There's also a cycle checker, which you could probably describe in like 30 seconds, if that, which is just as you're building something, anytime that you start building something, put it in this set of builds that you're working on, and at the beginning of it, check and see if you've already started building it. If you have already started building it, then that means to build the thing, you have to build yourself, and so that's a cycle, and so we crash. And so you just do that at the top of everything.
Yeah. Yeah, so there's this bookkeeping that's like kind of tricky to get right in each of these build arms, but there are a finite number of build arms. We just have to make sure that they all call these things correctly.
Yeah.
And then we're done.
Yep. And that's about it. And I'm at time.
All right.
Well, but I think we just about covered forward. Yeah.
Yeah. That covers it.
Yep.
All right.
Alrighty.